Okay, so this is class 2, continuing in fluid mechanics. We're dealing with stuff in chapter 2. I believe this is video 5. I hope this is the last video. Otherwise, I'm tired of hearing myself talk. So we're covering viscosity. These are fluid properties in chapter 2, and we're talking about viscosity. This is a really important fluid property, and these are slides from Sengel. I won't read all of this to you, but you could think of viscosity as the heaviness, the stickiness or the fluidity of a liquid, right? Or it actually could be a gas, true. And but you could think of the viscosity as also as something that is the resistance to shear in a fluid, right? We define fluids as being compared to solids is that they couldn't sustain a shear force, right? So if you apply a shear force to a solid, it can, as long as you don't exceed its strength, it'll hold and you can get to equilibrium. But that's not true with a liquid. If you apply a force to a liquid, a shear force, no matter how small, it will move. It just can't hold and stop that shearing force. And it's also sort of like a resistance to deformation as listed here. And air is much less viscous than water is, right? Here are some properties from the table that you'll use. You have to watch out for the units that are involved in here, especially when you're comparing it to the units that are in our textbook Sengel. We'll talk about that some more, I think. And so here's for the liquids and here's for the gases, right? And you can see, like, well, let's take a look at water is, and oh, by the way, we have two different kinds of viscosity that are provided to us. We'll describe what that is here in a second. But let's just take a look at the values. You can see that water is like 2.34 e to the minus 5 pounds second per square foot. Take a look at air instead. You can see that it's 3.74 e to the 7. So you can see that it's like at least 100 times different, right? Or maybe even more, but sort of on that scale, right? 2 orders of magnitude. So this is a diagram that's quite most often used when describing viscosity. It's like you're imagining 2 plates with this little gap with your fluid in between them. And we talked about the no slip condition. So at each of these plates right here, at that first molecule, it will move with the speed of the plate. The same thing true with this first molecule touching this plate. It'll move with, it will not slip, right? So we'll have a velocity of 0 if this is a stationary plate, and we'll have a velocity when we're using U here for some reason. Not to be confused with internal energy. It has nothing to do with that. They just sometimes use U for velocity. Don't ask me why. It just gets done that way. So anyway, this molecule right here, or all the ones that are touching the plate, will move with the same velocity of the plate. Therefore, there's a change in velocity within this fluid in this little gap, which they decided to call L for some reason. So there's a velocity profile, and that's an important thing, this velocity profile. That means the velocity changes with the height, or even you think of it as thickness, of the fluid in this arrangement right here. There's a force that's causing this velocity. And if you took a look at where the interface between the plate and the liquid is, that there's an area right there. And that force and that area are in line with each other, right? And that's the idea behind a shear force, right? Or a shear stress, right? Anything that's shear, that means that the forces are aligned with the plane in which that we're looking at the thing, right? I don't know if I want to, I think I want to come back to these, right? So let me go to my notes and start working through those. So viscosity, or at least the main one we're going to talk about, we principally talk about dynamic viscosity, and there's kinematic viscosity as sort of like a convenience. So if we want to take a look at the shear stress, let's refer to the shear stress of something. As we knew from mechanics and materials, we use tau and we take the shear force and the shear area, right? And those are the areas that are in plane with the force, right? They're aligned with each other. So our definition of viscosity is dynamic viscosity. We're using mu, is du dy. And what we mean by that is that's the slope right here with respect to the vertical axis. So there's y is the vertical axis here, u is the speed, so the speed of this. And now this first diagram assumes this linear line, but it doesn't quite work that way. We're treating this like it's a really, really small gap. But like if we have a flow over a solid body as shown right here, the velocity right here, of course, is zero, right? There's zero at the surface, but then it increases, and at some point far away from where this body right here, it becomes the same as the velocity of the initial flow, right? Far enough away from the solid body, right there. So we have like a little curve that we could form. We could say if we met that curve, I'm saying the curve is formed by like if we superimpose a graph of the velocity onto the figure right here. Here's like flow through a pipe, right? So these aren't plates that are moving again. This is a plate that's moving, a stationary plate. This is a cross section of a hollow tube. You could see that we have the zero condition here at both locations, and there's sort of like a flow in the center, right? That's taking place. We'll talk about flow in pipes some more right here. Some of the viscosity is not only about the slope that might be like right here, but it might be the slope right there, right? Well, we have differing velocity slopes at different locations, right? Depending on where you put onto the thing, that slope changes in reality, as opposed to this right here, which we're going to treat like such a small gap that it's all just one slope for this no slip condition. Here's where I'll introduce the convenient kinematic viscosity, right? So this is the dynamic viscosity that we're used to, and it has units. Let's see, I'll go an arrow instead of having equals, an arrow over here. Has units of mass times length to the -1 and time to the -1, or more commonly, more useful, force length -2 and then time, right? So if we want to go to MLT versus FLT up above. For dynamic viscosity, this is kinematic viscosity, what they do is they take mu and divide it by density, because so often we want to know those two traits so they get lumped together, right? So it's going to be, it's just that we're like using this for convenience, and that has units of length squared and time right here. Boom. And how this is measured is what they'll do is they'll take a known, most often they'll take a known volume, right? They'll have like a little can of a fluid, and then they'll pour it in here, and then they'll have a stopwatch right here, and they'll measure how long it takes for this thing to flow all the way through at a given temperature. Right, and then so by timing the thing, they'll actually have units. Sometimes they'll go seconds, centistoke, and that kind of thing. I think seconds, redwood. There's a bunch of other different viscosity means of measuring viscosity right here. But what we really care about more is this kind of viscosity there. And I found it's a little difficult to try to move from the practical viscosity to the engineering calculation viscosity. But anyway, something we should point out is there's a Newtonian fluid is one that behaves where the shearing stress is actually linearly related to the shearing strain right there. Another way to think of it, for a Newtonian fluid, it's the same regardless of the velocity that we move through it. It's easier to explain it by way of a non-Newtonian fluid. So example of a non-Newtonian fluid is cornstarch solution, which often is gravy. Gravy is thickened up often by adding cornstarch to the liquids that drain off from whatever. It could be turkey or sausage if you're in the South for sausage gravy. But the cornstarch, the flour will help, but the cornstarch really. And what you'll notice, so maybe you could try this out, is if you were to stick a finger in the gravy, and nobody mad, and you move at a constant velocity right here, it's easy to move your finger through. But if you try to move your finger fast through it, it'll be much more resistance to your motion. So the viscosity is actually dependent on the velocity in a non-Newtonian fluid. It's an interesting thing, but maybe not terribly. But anyway, you could probably demonstrate this if you have the right situation at the Thanksgiving dinner table. Wouldn't try it without figuring out, do the demo first in practice to see if you can get the results that you want. I don't want you embarrassing yourself in front of Uncle Stu, who is going to say, oh, they don't teach you much in engineering school, do they? That's how Uncle Stu sounds, apparently. So anyway, let's have an example here where we have this plate, and it is sliding down on its own accord at let's say it's a constant velocity of 2 centimeters per second or meters per second. By the way, this is an example I got out of Crow and Elger's textbook. You should check out their book. I appreciate I'm borrowing it. And anyway, this plate is 1 meter by 1 meter, and it weighs 25 newtons, and it slides down the slope at this with 20 degrees at a velocity of 2 centimeters, I hate centimeters, per second. The board is separated from the ramp by a thin layer of oil. So there's oil inside there. You just can't see it because it's very thin. With a viscosity of 0.05 Newton second per meter squared. Neglecting the edge effects, calculate the space. So how much space is in between those two things if we're observing this thing is moving at that speed? So one of the first things that we should do is do a free body diagram. And I guess I'm going to have to make a last video, even though I don't want to, for this topic. For this class, because this video is already getting longer than I like. But anyway, we're going to write this FBD, and here's the weight of this thing coming downwards, and it's at 20 degrees, so this angle right here is also 20 degrees, and there's going to be a normal force. This is really going to be the oil pushing onto the here, so I'm just drawing it as a simple force right there, and then we're going to have a shear force that's resisting right here, and let's do this as an X prime and a Y prime direction. We don't, all right, so I think I have everything I need there. We're assuming this is a constant velocity, so we didn't need an IBD. We didn't need the inertial body diagram, just the FBD. So the sum of the forces in the X prime direction, we don't need to have the Y prime direction, because we're not looking at the coefficient of friction, right? We don't have to worry about that. We're just looking at the viscosity. All we really want to try to do is get what the friction force is based on this. So we're going to have a negative. They gave us the weight. Yeah, no, they gave us the weight. So we have 25 newtons is the weight of this thing. But we need to take the sine of 20 degrees, right? Because it's only going to be in the X prime direction. And of course it's negative because it's boom, boom, boom going that way right there, the weight, but the friction force is going boom, boom that way, it's positive. So we're going to have the friction force equals 0. So the friction force is simply going to be 8.550 newtons. So we take our shear stress is going to be this divided by the area. So that's simply going to be 1 divided by 1. That's exciting. Right, because that's the shear area, is the area that the thing is running against. So 8.550 and these are Newton per meter squared now. And then we're going to say this is going to be equal to mu and du dy. And so we're going to assume a thin layer of constant. No, we'll just say a thin layer. That's good enough. We know what we mean. So that's going to be 8.550. Let's keep the units in here. Newtons per meter squared is going to be equal to mu, which is 0.05 Newton seconds per meter squared times du dy, but it's thin. It's a thin layer, so we're going to say that this is just going to be the velocity, or 2 centimeters per second, which is the same thing as 0.02 meters per second. Running out of room. And we're going to say that that's going to be y, which is the thickness. We'll call y the thickness. We run through those numbers, and we're going to get 1.170 e to the minus 4 meters, which is 0.117 millimeters thick. And that's our answer. And our video went a little longer than we wanted to, but exchanged a lot of information. Do we have anything else that we wanted to cover in here? I think I did want to mention how sensitive, or here you go, there's the non-Newtonian fluid, right? So here's the shear stress, that tau versus the rate of deformation du dy, and it's a straight line. And that's Newtonian, but you can see that some aren't a straight line, and those are non-Newtonian fluids, like when the slope changes with that deformation rate. And then we also see that we have some units, things we have to reconcile. A kilogram per meter second is what's given in the book here for viscosity in this one table, versus absolute viscosity right here, which is also the dynamic viscosity of Newton second per meter squared. We could work that out. They should end up being the same thing. And lastly, the effective temperature on liquids is a high temperature makes the viscosity drop for a liquid, whereas a high temperature for a gas makes the viscosity increase. That's sort of an interesting thing that you might not have recognized. All right, so we're going to have one last video that goes on surface tension, capillary action, and that should not be a long video because we're not really going to cover that topic much. So the end of video 5.